Hello, everyone. It's me, Billy Younger again, and I'm here for Physics Solutions, and we're working on part 6 of the vector addition series that I'm making. We have now resolved vectors A, B, C, and D into their components. I'm going to copy those components over onto the sheet of paper that my document cam is showing. It's actually already been copied, and we're going to make some sense, make sure we actually got the right signs for each of the components, and then we're going to add them to find the new x component of the resultant, and add the y components to find the new y component of the resultant. And then we're going to build that vector into a vector whose magnitude we know and whose direction we know. And we're even going to entertain various ways we could actually specify the direction. So to do that, let's go ahead and start by sharing the screen so I can show you the vector problem we're working, and I'll go back and forth between the sharing the screen and the document cam. So first off, here's the vectors that we're working with. We had the 20.00 newtons at 30 degrees. Notice that means 30 degrees measured counterclockwise from the positive x-axis. So that puts us squarely in the first quadrant where x and y are both positive. Remember, vectors, we normally think of them as their tail sitting at the origin of the coordinate system. Even when we're doing it by graphing, we always would take the first vector and put the tail at the origin, and then at the head of the first vector we put another little coordinate system, another xy, with x parallel to the original x and y parallel to the original y axis, and we draw vector b. So we're always thinking of it as the vector has its tail at the origin. This says that this is at 30 degrees. 30 degrees means it's closer to the x-axis than it is the y-axis. So you expect the actual x-axis to have the largest, or the x component to be the largest and the y component to be short. If it was 45 degrees, we'd expect the x and y to be equal in magnitude. If it was above 45 degrees, we'd expect the y to be greater than the x. So let's look and see if this matches what we got in our original problem. 20 newtons at 30 degrees, we expect it to be a bigger positive x component than the positive y component. So we'll stop share, look at my document cam, or I'm just going to turn it off because I'm a goober. And now I'll turn it back on. Okay, so we see we do in fact have a positive and a positive, and in fact the x component is in fact bigger. And being that's 30 degrees, we expect it to be, and it's 20 newtons instead of 10. We expect it to be a factor of 10 bigger than the square root of 3. That's exactly what that is. And we expect this to be a factor of 10 bigger than 1, and that's exactly what that is. So now let's look at vector b, which this says we got equal components but opposite signs, the x being negative and the y being positive. So let's look back at our original problem and see what b looked like. Here it is coming up. So we see b was 14.14, which looks a lot like 10 times the square root of 2, or actually, excuse me, 100 times the square root of 2. No, I was right the first time, 10 times the square root of 2. And that's at 45 degrees west of north. So that means you're going to take due north, which is this way, and you're going to go west, but you're going to go literally halfway between the y-axis and the negative x-axis. That's going to give us a negative x component and a positive y component. But since it's 45, we expect both to be equal. And that was exactly what we got. We got bx was negative 10 and by was positive 10. Now let's look at c. C is 50 newtons at 231.34 degrees. Now 231.34 degrees is again the mathematical way of saying it. And the largest axis angle that you can get to that's smaller than 231 is 180. So you go 0 is the x-axis, 90 is the y-axis, 180 is the negative x-axis again. So this is bigger than 180, but not quite 270. So let's subtract 180 from that, and we'll see that we get 51.34 degrees. 51.34 sounds like the 3-4-5 triangle. And of course, the 3-4-5 triangle has a 5 as a hypotenuse, and this looks like someone's multiplied 5 by 10. So what we expect here is it's 53.1 degrees below the negative x-axis. So with this one, we actually expect, since the 53 degrees is between it and the x-axis, the y component should be the biggest, but in magnitude, but negative, and the x component should also be negative. but smaller. So we expect probably -40 for the for the y component and -30 for the x component. So let's check and see if that's what we got. I'm gonna stop sharing. It does in fact say cx is -30 and cy is the bigger of the two, -40. So that makes some sense. Now D, it says we got a +24 and a -7. That should be a very small angle. And since the y is negative and the x is positive, that's got to be in the fourth quadrant. And it requires us to go a long way this way and then a short distance this way, like less than a third of the way. So we expect this angle to be really, really small and below the positive x-axis. And let's check that and see if that's exactly what we had. I'm going to share my screen again for the last time. And we see that was in fact 25 newtons at a compass heading of 106.26. Now remember, a compass heading is 0 when you're headed north, it's 90 when you're headed east, and this is a little bit more than 90. In fact, it's 16.26 degrees more than 90. And that 16.26 is in fact an angle from one of our Pythagorean triangles, specifically the 24/7/25 triangle. So yes, we do expect the x component to be very big and positive. We expect the y component to be very small, less than a third, and negative. So that all seems to pass the muster. It looks like these are in fact not only correctly copied, but correctly done. So now that we have that, all we have to do is say, and some people, by the way, take the time to make an actual table. You can do that. You can put a column for the vector names, a column for the vector magnitudes, and a column for the vector directions, and then a column for the vector x components and a column for the vector y components. And then below the main vectors that you're adding, you just put another column for r, the resultant, and you just fill it out that way. That's perfectly fine. It's just a little more. That might be helpful if you're doing like 25 vectors or something. I don't usually waste much time doing it, but what we now have to do is we just add these, and these signs are very important. That's why it's so critical that we always make sure they are in the right direction, even after we've worked out the mathematics of all of it. So this is 17.32 minus 10 minus 30 and then plus 24. Believe it or not, that still is a positive number, and it's not a very big positive number. It's a very, very small 1.32 newtons, and it's positive. So notice we're adding numbers. So the one with the least number of decimal places dictates it. Well, they all have 2 decimal places. So the sig figs here has to end on two decimal places. Again, using sig fig rules, which a lot of instructors don't care about, at least in their lecture portion. Now the r sub y, I have to add these as well. That's plus 10, that's 20, minus 40, that's -20, minus 7, that's -27. So this is a negative y component, and it's 27.00 newtons. Again, 2 sig figs, or 2 decimal places is right. That makes perfect sense to what we got. Now all I have to do is build an actual vector out of this. Okay, so I can have a magnitude and direction, because generally if they give you vectors in terms of magnitudes and directions, they generally expect you to give them back to them in terms of magnitudes and directions. However, I'll show you other ways to write it as well. In the calculus-based physics class, they sometimes just allow you to write the x component times I hat plus the y component times j hat plus the z component times k hat. Or if you ever forget that, most instructors are cool with you writing the x component times x hat plus the y component times y hat plus the z component times z hat. So what I'm going to do in order to figure out what this vector looks like is I'm going to draw a coordinate system. I know I have a very small x component, but it's positive, and I have a very big y component and it's negative. So I'm definitely going to be in the fourth quadrant. I'm going to draw, this is my x-axis, and I'm going to draw my y-axis as this pointing up, of course. And then we need more of it down here. Now I'm going to measure this angle from the positive x-axis, and if I measure it down this way, I can just report it as negative whatever the angle is. So when I do it that way, that suggests that I should first go from the origin along the x-coordinate axis, or along the axis. And I'm going to not really make it that good to scale. I want to make it big enough for us to be able to write above it and stuff like that. That one is in the positive direction. It's 1.32 newtons. And then, of course, the other one, putting it at the head of the first vector, we'll get negative 27, and this should be straight down. And it should really be even longer than that, because this is only about 1.5. It's less than 1.5. So this really should be more than 9 times as long as that thing. But that's okay. The main thing is to get, whether it's closer to 60 or closer to 45 or closer to 30. That's a pretty good way to make sure you haven't made an error. Now, what that means is the actual vector is from here to here, which when you go to draw these things, it's often a lot easier to hit the mark if you use a straight edge. So I'm going to go ahead and use a straight edge just to keep from looking so gooberish. So that's the vector R right there. So vector R obviously points some angle phi is what I call it. Anybody knows whether that's supposed to be pronounced phi or phi, please let me know. Preferably someone who knows stuff about Greek. That would be nice. Anyways, so there's the X component, and of course the Y component. I didn't write the number down here, but it's 27.00 newtons. So 27.00 newtons is what that is, pointing in the downward direction. Hence, I've got everything as red and green. Red for the for the negative and green for the positive. Now, if I can keep this notepad from sliding. So what I need to do is I need to combine these two to give me the length of this. That's just the Pythagorean theorem. So that means the magnitude of R, which we can write as R vector in absolute value bars, or we can just write with the symbol R with no vector symbol. That's equal to the square root of 1.32 newtons squared plus, notice I'm putting this negative 27 in parentheses because we got to square the whole thing. If you randomly put this in your calculator and just put negative 27 squared without parentheses, for instance, it's going to give you a negative number. And then you'll get a negative number under the square root, because clearly 27 squared is way bigger than 1.32 squared. But you should never get a negative under the square root when computing the magnitude of an actual vector. Magnitudes of components can be positive, negative. You're never going to have a negative magnitude of a vector. But you're going to add all those. You're going to take the square root. Turns out that's going to be the square root of 730.742 roughly. Newton squared. It actually goes on quite a bit further than that. The main reason I like to do this separately is I do 1.32 squared and I figure out what those 3 sig figs get me, because I'm multiplying, so this 3 sig figs is relevant. And then I figure out what the 27 gets me, and it turns out I get 1 decimal place, and that's it. Okay, because basically these 3 sig figs makes a small number, so I'm able to get the 2 of those, but this one makes a big number, and these 4 sig figs just gets me 1 past the decimal. So it's literally only 1 sig fig or 1 decimal place that I get to report on this. The answer turns out to be a magnitude of 27.032. And I underline the 3 and the 2 just to remind you that those two are not significant figures according to sig fig rules. Now, I can also say that if I take the tangent of phi, that's opposite over adjacent. Notice I'm not going to use any signs. I'm just going to use opposite and adjacent without any signs. So I'm going to say phi is equal to the inverse tangent of opposite, which is 27.00 newtons, over the hypotenuse, which is 1.32 newtons. And when you take the inverse tangent of that, you end up getting 87.20 degrees. Of course, that's only 3 sig figs there, so technically we're only supposed to use it up to the 87.2 degrees. Okay, so how do we express this vector? Well, we can say the vector R is 27.0 newtons at negative 87.2, or excuse me, 0.3 degrees. So that's negative 87.3 degrees. Sorry about that looking so terrible. Another way we could express that, and notice I said it's negative because it's measured clockwise from the positive x-axis. That's the definition of a negative angle. I could also say, well, I go 90 from north to east, and then I go another 87. So 90 plus 87.2 would be 177.2. So I could say 27.0 newtons at compass heading we said that was going to be what, 87 or 177.2. Oop, I shouldn't put that 0 there. Sorry about that. So it's 177.2 degrees. Another way I could say it is it would be 27.0 newtons at, let's say, 87.3 degrees. And that was supposed to be 3.2. Sorry about that. So technically, this should be 177.3. Sorry about that. So that's 87.3, but that is actually measured south of east. So that's an acceptable way as well. You could also take 90 minus 87.3, which would be 2.7. So you could say it's 27.0 newtons at 2.7 degrees. And that would, of course, be east of north. Or excuse me, east of south. Oops. East of south. Sorry about the getting all screwed up there at the end. But yeah, those are all the ways that you can do it with all these different compass headings and whatnot. Now, you could also use the way we do in calculus-based physics, which is really wonderful, and you wouldn't even be required to do this last step. That's why a lot of instructors say, hey, if I give you even one of the vectors in magnitude and direction format, I want the answer back in magnitude and direction format. So we could also say R is equal to 1.32 newtons in the I hat direction minus 27.00 newtons in the j hat direction. And I just means a unit vector in the positive x direction. And when I say unit, I mean it's just a pure number, pure unit length. And this is the same thing, but in the y direction, that's what the j is. And then there's a k hat, and it's the same thing in the z direction. Or we could also use, because a lot of times students just forget which one's I, j, and k, you could say it's 1.32 newtons x hat minus 27.00 newtons y hat. And then other ones just use things like E1, E2, and E3. So they literally put a lowercase E1 for I, a lowercase E2 for J, or crazy stuff like that. All those are acceptable. And that's the way you can go about adding vectors and then resolving them in components. You can see this last step is really, the addition part is the easiest, but then, you know, all the ways you could possibly decide to measure an angle, that gets a little hairy. If the particular homework system you're using or the instructor itself has asked for the angle, let's say east of south, remember I made that mistake there, east of south, then what you would have preferred to do would be put the 27 newtons downward first and then the 1.32 there. Then you can see that this angle right here is the one they want, and you take the inverse tangent of that, which is 1.32 over 27, and you'd end up getting that 2.7 degrees that we found the other way. So that would work as well. That's good enough, but let me give you something to try. Again, now that you have all this, you might want to stop and see if you can work it all out yourself. But when you're done with that, I suggest you try the following. Try finding the resultant of, we'll call this R2, which equals V1 plus V2 plus V3 plus V4 plus V5. So these are the 5 vectors we gave you in parts. Basically, I think parts 1, 2, 3, 4, and 5. I think we gave these to you. It might have just been 2, 3, 4, and 5 that we gave them to you. But you've already, supposedly, if you were doing the work along with it, as you should have, you should be able to find the, already have all the components broken down. Then you just have to add all the X components to get the new X component, add all the Y components to get the new Y components. Here's a good time for you to pause the video, try to work that out. And here's the answer that I got. I got R2X was equal to 30 plus 10 minus 86.6 0, check my work too, of course, minus 20 plus 14. And that gave me negative 52.60 newtons. And I got R2Y equals 40 plus 10 plus 10 minus 20 minus 48, leaving the units off again just to make it easier to write all this. And that gave me a positive 32.00 newtons. Of course, when I put that in a coordinate system, that looks more like I'm going to be in the second quadrant. So this would be my x-axis here. This would be my y-axis here. And these are pretty close to the same size, but the y component's a little bigger. So I would draw, say, the y component being in the positive direction as, actually the x component's a little bigger, as this, and then the x component being negative, but quite a bit bigger, as being this. And then this is your vector R2, and you can compute this angle right here, theta. And when I did that, actually, no, I calculated this angle, phi. When I did that, I got R is equal to, this R2 magnitude is equal to, that magnitude is supposed to be 61.06. And that angle, since I've shown you the angle, I can just say at, it's going to be this angle at phi equals 31.32 degrees. That's it. I hope that helps you. And going back through all these homeworks as you're going along will really help you. And just, come back and visit this anytime you have a problem with vectors. I hope you all found this helpful, and tell a friend about Physics Solutions. Talk to you later. Bye-bye.